So looking at example 311, we're asked to calculate how much glucose someone would consume during a marathon if they ran a marathon for a certain length, and that would consume a certain amount of calories, or a number of calories. And we're given some information about glucose under biochemical standard conditions, which means we're working at 310 Kelvin. So biochemical standard conditions is, of course, something else to normal chemical standard conditions. So you just need to make a note of that. And essentially, if we think about what gives us an indication of something that's able to do work, that is the Gibbs energy. The Gibbs energy gives us the amount of free energy that's available to do work. And our bodies are a constant volume system, because your body's volume doesn't vary that much. So that's how we will approximate this system. So we'll work with a constant volume system, and we'll use the Gibbs energy to tell us how much free energy is obtained from the burning of glucose, or the oxidation of glucose. Right, which is essentially the burning of a hydrocarbon is also called the oxidation of that hydrocarbon. A more practical example will probably be something like petrol in a car, or burning that kind of thing. That would give you a more realistic example than there's very bad dietary advice of eating that amount of glucose before a marathon or for a marathon or whatever. But anyway, this is just an example, so let's do that. So let's start by calculating the Gibbs energy to find out how much energy is actually obtained from this, or is actually obtained from 1 mole of glucose per 1 mole of glucose, right? As remember, we're going to work with molar quantities, so it will give us an indication of how many moles, or how much energy per mole glucose we would obtain. So I'm writing reaction because, of course, it is an oxidation reaction that takes place. So the burning of glucose in your body would be an oxidation reaction. This is minus 2816 times 1,000 because it's kilojoules. So we want to work in joules. This is minus, we're working at 310 Kelvin. This is 285.8. Yeah, 285.8 joule per Kelvin per mole. So the kelvins will cancel, and that gives us a value of minus 2872 kilojoules per mole. Right, now I've rounded, but you shouldn't round. Okay. So that gives us an idea of how many kilojoules we'll get per 1 mole of glucose. Okay, but we're given the energy expenditure in kilocalories, so we also need to get kilocalories into a unit of kilojoules so that we can work with that. So in other words, how do we get kilocalories to kilojoules? So 2,500 kilocalories. How many kilojoules are there in a kilocalorie? In a kilocalorie, there is 4.18 kilojoules in 1 kilocal. So in other words, we just do this multiplication. It gives you 10,450 kilojoules in 1 kilo, or so many kilocalories, right? And you see the nice little abridged method I use, so that tells you those cancel. In other words, then you're left with kilojoules as your unit. Okay, so now we know we need so many kilojoules, and we know that this gives so many kilojoules per mole. So if we divide those two quantities, so we'll just make this an absolute value. So we just take the positive of that. In other words, we just quickly do a calculation on the side that says 10,450 divided by 2872 gives us roughly 3.64 mole. Oops, daisy. Mole. Why does it give us mole? Because we have kilojoules here, and here we have kilojoules per mole. So the kilojoules cancel, the mole goes on top. And then we're left with so many moles. So in other words, that's the number of moles of glucose that we need. Right. And that, of course, then you can calculate that many moles corresponds to 656 grams of glucose, because we have about, in 1 mole, it's 180.2 gram per mole. For glucose, this is molar mass. Okay, so I think this is relatively straightforward. It's mostly this initial argument, just to remember that the free energy comes from the Gibbs energy. So in other words, that's all you basically require. Once you've made that connection, it's very straightforward. This is the application of the formula, and then just the conversion of the energy to the correct units. Then you should be fine. As final step, I mean, you just basically, you know how much is there in 1 mole, so you just want to figure out how many moles you require. Okay, I think that's it for this example.